Okay, welcome everybody to this new Ithaca Fest episode. Today, first, we are glad to have as first speaker Greta Coraglia speaking about Comonads for dependent types. To you, Greta.
Thanks, and also thanks for having me. And it's always a great pleasure to take part into Ithaca things. So it's very nice to be here. Okay, so as Gabriele said, I'm going to talk about comonads for dependent types. And as I mentioned off screen, something broke in my presentation before we started, so I apologize if something was wrong, but we'll see. Okay, so first of all, what are dependent types and why are we so interested in them? So dependent types are something that we use when we want to have types that depend on terms or they vary with terms. So the most popular and say most easy example is that of vector spaces. So for example, we might want to be able to express the type vect n of k vectors of length n, where a small n is a natural number, so is in itself a term of some type n. So when we write these in forms of a rule or a deduction of some sorts, this is kind of what we try to do. So we break apart the term, and then we want to express out of this type vect, which is depending on n, a new type. So if we abstract a bit from this is the rule that we are kind of accustomed to seeing, which is sometimes called dependent typing, sometimes called substitution, but I'll use the word dependent typing because it's more suited for today's purpose. So I use colors to detail the relation that we see connecting the three parts of this deduction or this rule. And somebody try to unmute me. I'll see. Okay, and what I want to see with you today is that actually this relation that allows for such a deduction is inherently comonadic in some sense. So a first attempt into modeling something of this kind is that of a morphism in a locally Cartesian closed category. The problem with this approach is notoriously a problem with coherence, because what is substitution is interpreted to pullback, and this leads to some issues in stuff being, rightly suited in one sense or the other. So a more sophisticated solution, I'd say, is that you take a category and just put structure in it and see what you can do to interpret the dependent types. So I want to start today by looking at two models. One is very known and popular, and the other one is pretty new, but I hope I'll convince you that those are also interesting in a second. So the first model is that of CE system, and you can, if you know about C systems or contextual categories, you can think of that as just an unstratified version. So you need two street category structures, F and C, with objects, with the same objects. So two category structures on the same set or collection of objects, and then an identity on objects functor from F to C, a chosen terminal object in F, and for any sigma from theta to gamma in C, a choice of rulback that does the work, plus equation that we're not interested in at the moment. The other model that we're going to talk about a lot today is that of comprehension categories. In a sense, it's a little bit tighter and maybe simpler. So we start from a category and we ask for a functor from some other category E into C arrow, such that the composition, which we call P, is a Grothendieck vibration, and Chi sends Cartesian maps, so P Cartesian maps into Pullback squares. Oh yes, that's supposed to be on the other side. Apologies. Okay, so these are two categorical models, and first I want to focus on how these two model dependent types. So how do we interpret the fact that gamma is a context? That we do both considering context objects in the base category that we have, so C. Then we model the judgment that A is a type in context gamma by saying on one hand that A is an object in F such that if we take its image, sorry, A is a morphism in F, such that if we take its image through I, and then we kind of collect the codomain that we obtain gamma. And on the other side, it's maybe easier. So the fibration P, so A is in the P fiber of gamma. What about context extension then? So out of a context and a type, we want to compute some new context. So on one side, this is computed as the domain, and on the other side as well. So we can think of it as both interpretation being very morphism-like. So really, a type is its context extension. And what about terms then? So how do we say that small a is a term of type big A in context gamma? Well, since everything is very, say, morphism oriented, then terms are sections. In one case, there will be sectional of 5A, and on the other of the image through chi of A as an object. So I want to spend a few minutes to discuss some examples of this. So comprehension categories are kind of known. So the first example is the kind of the syntactic one. So we consider C the category of alpha equivalence classes of contexts and terms. And then we collect in the category E type judgments and substitutions. So that chi is precisely that computing the projection. So the syntactic example is an instance of such a construction, but there's more. So another one that might be interesting, and it's very again map oriented, is display categories. So if C is a category and D is a collection of morphisms in C, such that it has pullbacks along any map and it is closed for such a construction, then the inclusion and there should be an arrow sign, but the inclusion is itself comprehension categories. So certain class of maps also are good for describing context extensions in the perspective of comprehension categories. Another maybe say less informative example is that of simple fibration. So if we have a category with products and we compute the simple category on C, then we can define context extension as being the one that produces the simple projection. So again, this is the least informative context extension, but still it's a model of it's an example of a comprehension category. And finally, one example that may be closer to the logicians in the audience. So if we consider a topos and its sub-object classifier, then the comprehension is comprehension in the sense of the comprehension categories. So we have many examples, but historically, there's also be another perspective on this, and in a sense, it's also reasonable. So what if we consider terms as separate objects in some sense? So this is what happens in the case of categories with families and of natural models. So types are considered sets indexed over context, and terms are sets indexed over types. And this kind of makes sense if we think about the rules that we started from, because we kind of have two different kinds of judgment. We have judgments concerning terms, and we have judgments concerning types. So even if they are related, they have to be dealt with in a kind of a separate way. And so the intuition is that we want to encode the entailments or the context relation in a discrete vibration, and then rules kind of have to be commutative triangles. And I hope to convince you of that in a second. So we will have a category U dot collecting all terms, and a category U collecting all types. And then we have a relation connecting types and terms, and that is the sigma that you see there. So we write that A is a type in context gamma if the object A is in the fiber of gamma, and we say the same for small a, and the typing of small a is computed by sigma. So why triangles? Well, if we want to relate fibrations, then we're going to need morphisms of fibrations, or so in particular, they're going to be some sorts of triangles, so special triangles, let's say. So in particular, if we try to read a rule into such a triangle, we have, and why would we want to, let's say, read a rule? Because we start from a judgment of this kind, and we get a judgment of this kind. I hope you can see my mouse, but the point is that if we have a term small a, then its type is itself in context gamma, because we ask of this triangle to be commutative. And this is the intuition behind both categories with families and natural models. But so we try to shift the perspective some more, and the first question that one might want to ask is why discrete? Because many examples that, is that a question? I heard some, okay, I'll just keep going. So why discrete? Because it makes sense to consider types to be collected in sets, but we might be interested in seeing the morphisms between them. So many examples actually that we started from comprehension categories are not discrete, and still it looks kind of like that does some job at interpreting context extension. And the second question is, well, okay, so if we can encode some rules into diagrams, does it mean that each diagram that we can read out of some sort of, let's say, operation starting from some basic things is a rule? So if a rule can be encoded in a diagram, does it mean that we can point at some classes of diagrams such that each diagram here denotes a rule? So this is a second question. And then what does it mean to manipulate rules? So this is kind of connected to the second point. And what is the minimum deductive power in terms of diagram that we need, if so? So these questions are kind of what simulated the introduction of judgmental theories in a work joined with Ivan. So we encode relations in a possibly non-discrete vibration, just to, we don't need to choose at first. And then rules are going to be lax commutative triangles. Why lax? Because we cannot be sure that the we'll see in a second, but the point is that context might not be precisely constant through the deduction. So this is what motivated the definition of judgmental theories. So they're defined in steps. So we define basic entailment encoding vibration or context encoding vibrations, such as U and U dot. And then we define basic rules relating them so that we know in what relation they are to one another. And finally, the deductive power is encoded into the system using categorical constructions, such as the one below. So for example, we can code pairs of terms of the same type. And then when we compute their equalizer, we know that there is a unique map out of the diagonal such that these commute. And so these we can read as a rule. It means that we start from something of this kind, we end up with something of this kind. So it means that we read a rule such as this, which is a rule that we might be interested in. I know I said a lot of things about judgmental theories in a very short period of time, but there is another talk about it if you want to see the subject in more detail. So this is not, this is just to introduce and motivate the definition. But what we're interested in now is the definition of judgmental dependent type theory. So we say that a pre-judgmental dependent type theory is the data of vibrations U and U dot, a morphism of vibrations sigma, and delta a right adjoint to sigma with Cartesian unit and co-unit. So this delta will be the one performing context extension for us. And then so we have something, we want to encode some deductive power because we want to be able to calculate diagrams. And so we say that a judgmental dependent type theory is the smallest two subcategory of CAT containing all the things that we started from, such that it's closed under finite limits and sharp lifting. And by sharp lifting, I just mean the property of, let's say, pulling back two cells along the direction. And we have proved that a judgmental dependent type theory contains code for all structural rules of dependent type theory. So in this very syntactic, diagrammatic way, it is actually a good model, not only for dependent types, but the calculation that one does in it. So, for example, as I promised, the delta that we're asking to be right adjoint to the typing functor is the one that reads precisely as context extension. And what I meant that we want triangles to be lax commutative is that if you follow the map starting from U and getting to C on one side, this is when you get gamma dot A, while on one side you just get gamma. And oh, okay, there's a raised hand, but maybe I can take questions in a second. So this is just to say that we want these rule has an underlying context morphism, which is the projection of gamma dot A to gamma. So just to show you what is that, for example, if we want to code these pairs of judgments, then since we are closed by pullback, then we can compute them by simply taking these iterated pullbacks. And I apologize for this notation, which is a bit weird, but we just all you need to know is that, for example, if we start from here, so what is that it's coded here? So we have pairs, small a, and then small a goes through sigma to a, then is context extended via delta, so goes to u dot, and then we just forget everything but the context, so get gamma dot a. And then if we take something on this category and we ask for such a pullback here, this is what produces precisely the pair here, so the third pair, because we have such pairs of judgments. So the approach to this is very, as you see, very modular in the sense that if you want to complex judgment, you just need to perform iterated pullbacks and equalizers, and have what you need. Now, as you imagine, this makes type constructor much easier than they usually are, because we can see that we can know precisely what rules we need to encode, for example, pi types. Why? Because pi formation requires for us to have something that goes out of this complex judgment and provides a new type. So in terms of diagrams, it means that we want to start off something here, and out of this, we want to produce a new type here. And introduction asks that out of something of this kind, which is encoded via this pullback, we want to produce a term. And we want this to be commutative because we want the type of the term produces in the first row to be actually the one produced in the second row. So we ask that this is commutative, and we get that it has the correct typing. And then if we also ask that this is a pullback, we get elimination and eta and beta computation. So as you see, now it's very easy to see what we want to do if we want to try to encode new type constructors. So for example, okay, if we start from this, and we ask for such two red maps, then we get pi types. Now, what if we start from these two judgments, so which maybe you have recognized, and we ask again such two red maps? Well, this is the way precisely one gets identity types, extensional identity types. What about these? Again, we only need to compute this pullback. There's many pullbacks here, but as you imagine, but still, this is just a pullback. And so asking that the system has, in this case, some types, is just asking that there are two such red maps. And again, if we want unit types, we just ask that there are two maps out of the identity. But this is just to show you, and I'll try to provide an example of this before we end the talk. So the point is, where were we? Okay, we have two nice models. One is comprehension categories, and the other one is judgmental dependent type theories. And on one side, we have few assumptions, and on the other side, we ask a bit more structure. But in a sense, in the judgmental case, computations are easier to do. While in the comprehension categories, they're internal because we ask of properties of morphisms inside the category. And also, this makes it very easy to ask for constructors. So what is the relation between the two? Well, it actually is that there are two equivalent. So meaning that those comprehension categories and judgmental dependent theory encode the same precise amount of data in some sense. How? Well, there is one key observation that needs to be done here, which is that sections are coalgebras. So if we have a category D with pullbacks, then we can define a comonad of kernel pairs using the universal property and iterating the pullback. So we can define a comonad on maps that to a sigma, let's say, assigns its kernel pair. Well, not precise. Okay, the morphism sigma dot sigma again. And then we can define a co-unit and a co-multiplication. And in this case, coalgebras of such a comonad are precisely sections of sigma. So this gives us a way into connecting the two, because on comprehension categories, we had sections for terms. And in this sense, we now have kind of a particular comonad, which is the kernel pair comonad. And on the other hand, with JDTTs, we have sigma delta because we had a pair of adjoints. The relation that we can establish between the two is actually that of an intermediary category, which is the category of WC comonads, so weakening and contraction comonads. So let's take a fibration, then we call a weakening and contraction comonad on P a comonad on the total category such that each of the components of the co-unit are Cartesian, and for every Cartesian arrow, the image in C under P of the naturality square is a pullback square. So you can kind of see how this establishes a middle ground between the two. So first of all, a remark: this is a comonad only in some bounded sense, because actually the co-multiplication is canonically determined by K and epsilon, because the naturality square of epsilon at epsilon A itself is over a pullback and has two parallel Cartesian sides. So it is in itself pullback. So it's very much bounded in this sense. Okay, so we have a fibration and a comonad on the total category such that it has some interesting property. Why do we call this weakening and contraction? Well, the weakening part is precisely the co-unit. So this is what will be the extension part. Okay, so the weakening is a morphism, and you kind of can imagine it as adding a dummy variable to A and then subsequently to P of A. And the contraction part, of course, is so if we have two variables, then we can collapse them to one of the two. And this is just done by performing such substitution. And the equations actually are just expressing the fact that weakening and then contracting produces no result up to alpha equivalence, of course, because we have variables that change names. Okay, so we have fibrations and comonads on them, and they can kind of interpret weakening and contraction. And now we need to make them into two categories. So clearly, 2 cell is a pair PK, and I just omit the epsilon and the delta, a one cell is a tripole such that we have a morphism of vibration, so a one cell in phi, plus a lax morphism of comonad, theta. And then a two cell, you can kind of imagine what that needs to be. So we're going to need a pair of natural transformation phi and psi such that they interact well with the respectively theta parts. Okay. So this makes it into a two category, and we will write pseudo and strict for the two subcategories corresponding to what you can kind of guess. So we can also restrict it to say least informative subcategories. Now, first, I'm gonna try to give an intuition of how WC comonads are related to comprehension categories, and that it was actually first observed by Jacobs. And so he showed, he says that each WC comonad induces a comprehension category and vice versa. And on one side, you can kind of see that it suffices to take the Cartesian lift at the comprehension, and on the other side, you just define the you just define chi to be precisely p of the epsilon. And we have shown that these upgrades to a two equivalence, which then restricts to the respective subcategories. And maybe in literature you maybe seen the category of comprehension categories, but that was just we use that in this lax sense. So when we usually see it in literature is that of strict morphisms. Okay, so WC comonads and comprehension categories are neatly related. The WC comonads also act well with judgmental dependent theories. For starters, it's, of course, when we start from an adjunction, then we can define the comonad, which is actually sigma delta, as we said, which performs the extension. And of course, on the other side, whenever we have a comonad, we can compute the Eilenberg-Moore adjunction, and these we can show it extends to a judgmental dependent theory. And the key observation here is that any coalgebra for a WC comonad is Cartesian. So this is the key fact that makes everything work. And this is just a property, of course, of those comonads that are say related to vibration in this weakening and contraction sense. All right, so we upgrade these to two equivalence, which again restricts to the respective subcategories. So we want to start with a WC comonad, and if we start from there, we just get the identity performing the construction process. On the other side, what we get is the need to compare these two judgmental dependent theories. So on one side, we have U dot, and on the other side, we have coalgebras for these sigma delta common. And this is actually the key aspect that makes everything work. And we show that every term is a coalgebra and every coalgebra is a term. So clearly every term is a coalgebra because you just need to consider the image through sigma of the unit of the adjunction. So every term is a coalgebra, but the converse is also true. So to each coalgebra, we want to match an object of the category U dot. Remember, the category U dot, we had no previous idea of the structure held, but we can define this object A of H, so where H is the coalgebra we started from, as the domain of the U dot Cartesian lift of UH at delta A. So we start from H, compute its image through U, and get a morphism of context, And then since u dot 2 is a fibration, then we can compute this lift, and this produces this AH. Okay, and this goes fine for us because since this is Cartesian, and sigma preserves Cartesian maps, we have both H and sigma of this map here, and they are both Cartesian and over the same map, so they must be isomorphic. And by similar arguments, we can show that these precisely produces an equivalence of categories. So every term, even if we try to break out from the coalgebra from the section interpretation, is a coalgebra and vice versa. So again, these we can use to describe that we have two. So putting everything together, we can show that there is a two equivalence of the categories of comprehension categories and that of judgmental dependent categories. And what it means, or at least how I like to interpret this, is that actually the moment we chose to interpret weakening and context extension, so the moment we chose how to describe chi, then we have immediately bounded a lot of our interpretation, because contraction is now bounded, and that is just WC co-multiplication. And then terms are bounded because, as we said, every term is a coalgebra now. And hence, if we have a sound way of interpreting type constructors in a JDTT, it means that this is also bounded by the choice that we do for context extension, which is, I think, pretty reasonable, but also very, very interesting. So I spoke about C systems at the beginning, and there's one reason that I wanted to do that, is just to show you how we can use this these two equivalents to our purposes. So if you remember, we said that we have a C system is a sum of a lot of things, but in particular, we have a functorial choice of pullbacks performing context extension. So if the choice is functorial, it means that we kind of have something like this, right? So these, if you have practiced a bit with categorical models of dependent types, it kind of looks like a sum, so a dependent sum. So even if it's not stated into C system, it kind of looks like they have some encoded structure of dependent sum. And now that we have these two equivalents, we can make this statement precise. How? Well, first we relate CE systems to judgmental dependent type theories. Then we show that judgmental dependent type theories have dependent sums. And then we have proved our statement, right? So let's see. So we relate to, and in particular, there is the junction between judgmental dependent type theories with strict morphism and CE systems. And in particular, I want to just to describe to you what the right adjoint does. So to a CE system, we map the following judgmental dependent type theory. So the fibration is again that obtained by I followed by COD, and the WC comonad is that again induced by the kernel pair construction. So we just need to define a fibration and a comonad, and that is what produces the judgmental dependent structure. So these, so these provides the comonad that we wanted to, and so in particular to each C system we can match a comonad structure. Now let us show that the object that we obtain through this association produces the desired structure. So remember, and now I just use this kind of norm symbols because the pullback notation was a bit hard, but you can kind of see these again what we asked for. So we need to show that whenever we have something of a JDTT obtained starting from a CE system, that we can define such pair of maps. Okay, so we compute them. So we can compute the category of coding the premise of the dependent sum introduction. And you can see that when you try to calculate such a pullback, you get diagrams as this, so the black part. And as I mentioned, I almost broke the presentation when I tried to hide this red part, so please pretend you don't see it for the moment. But so objects of this category coding the premise of the introduction is this collection of maps. And the category only concerning types forgets about the top part and just keeps these two maps. So we can define, and it actually works, we can define sum and pair as the red maps. So we can match to A and B, this composition, and we can match to all of this, so small a, small b, big A, big B, we can match these, and this will be a new term. So what it means, what it means is that for every CE system, we can define a judgmental dependent type theory that that has the property of having dependent sums. And not only that, actually, every judgmental dependent type theory with dependent sums is equivalent through this adjunction to a CE system. So it means that having dependent sums is precisely what takes out of judgmental dependent type theories those that are CE systems. So this is new, this is interesting. So just to conclude, what we've done. So out of a pretty syntactic approach, I would say, but I know there's a lot of discussion about this. We have described a new model that allows for easier treatment of type constructors, because it's easy to know what to ask if you just need to encode premises using pullbacks and other limits. And so this makes it easier to compute type constructors, and then we have detailed its relations to previous models, and we can use it to describe the relation of one model to the other, and describe in particular how comonads come into play, and in some sense that there is no escaping sections. So even if we try to come out of asking that terms are section, we're going to get back to it eventually. But there is plenty to do, so I want to mention some ideas. So first of all, now that we have all fibrations and not only discrete ones, we can study subtype. And this is what I've been trying to do with Francesco Dagnino. And then we can use this theory to see what more structure one needs if you want to encode more complex type constructor, for example, inductive and co-inductive. And then if we want to consider judgmental dependent type theories as a calculus, we're going to need some completeness result, because we have validity, but now we need to kind of show completeness of such a calculus. And finally, the moment we have an adjunction, not only do we have a comonad, but we also have a monad. So maybe the opposite monad would be interesting in some way, and that we don't know. And with that, I have finished, and I thank you for listening.
Thanks, Greta. Well, are there any questions from the audience? If you do, please unmute yourself and ask the question.
There was a raised hand has been for a while, but I don't know if.
I think
Yeah, that was me. It was a really small question during the talk. It was when you define judgmental theories, you said at the same time it was a sub-2 category of cat, and that was the smallest such stat. So it wasn't clear to me why there could be several such.
Yeah. Okay, that I think I slipped there, because the point is that you start from something you know. So in this case, you start from terms and types, and they're related in some sense. And then the way you want to do calculations, you encode this deductive power through limits and sharp lifting, so lifting two cells along vibrations. So I think the point is that you either want to have the least number of deduction that you can have, and so you just precisely take the smallest that is closed under such and such, or you just ask that it's closed, but then you don't know nothing about deductions that are not of the form that they started from, in a sense.
Okay, so if I'm following right, a judgmental theory is A2 category, which is closed under finite limits and sharp liftings.
I say yes.
Okay, thanks.
Thank you. Sorry to keep you waiting for the answer.
No worries.
There was another question by Mili Maietti, I think.
Yes, thank you very much for your talk. I would like to ask you how flexible is the machinery of dependent type theories, judgmental dependent type theories? Because one issue about categorical modeling is that you cannot handle combinatoric version of type theory, where you avoid some rules, some conversion rules like the Xi rules, which is not validated in cleaning models, like usual intuitionistic clean interpretation of intuitionistic logic, intuitionistic arithmetic. So I was wondering whether your machinery could handle it. From what you said, it seems no, because lambda should be morphisms, but they might be. So I was wondering this. What a new application you have of your new machinery for modeling new calculus that before were not be able to be modeled. Thank you.
Okay, there is an excellent question. I'm not sure I know how to answer your question at the moment, but the point is that I think some work could be done, but I don't know precisely what rule you're referring to, so maybe we can talk this later. But the point is that how can I say that? So you're not forced to accept any rule that you don't put in some sense. So for example, there is no one way, there is no, for example, when you start with a categorical model, you, for example, the C system model, you have some notion of dependent sums that you didn't want at the beginning, but you end up with, right? And this doesn't happen in our model because you just have judgments and they're related in some sense. So you don't have constructors, you need to ask for them. So for example, as I said, you can find pi types and you can ask that square is a pullback. And if you ask that square is a pullback, then you'll have elimination and eta and beta computation, but you don't need to ask that it's a pullback. So for example, you can ask that it just commutes, so you don't have you have less rules, or you can ask that it's a Wilk pullback and you don't have eta and such. So I think some work can be done, but I wasn't aware of the problem. So if you can refer something to me, I'll very gladly read about
it. And if I may, another thing, instead of proving completeness result, it would be better to strengthening this result, to proving what I called in my paper modular correspondence type theory, to provide an internal language theorem. correspondence, namely by equivalence between models and theories of a certain kind of type theories.
Yes, that's the.
And you have all the machinery for the two categorical structure to do this if in a polished way, let's say, if it's possible.
Okay.
Thank you very much.
Thank you for the suggestion. It's very nice.
Jacopo, go on.
Yeah, actually, I mean, it's just a comment to Millie's question. I think that the issue here is how the definitional equality is interpreted, and in the usual semantics, as you say, is simply it's interpreted as equality. So every construction is going to be a congruence with respect to the interpretation of definitional equality. So every such model will validate the Xi rule, for instance. And I believe this is the same for judgmental dependent type theories. But yeah, I don't know. Maybe the additional data that you get moving from faithful vibrations, from discrete vibrations to arbitrary ones, can give you some room for changing things. But
maybe you can do like setoids, no? You put there something fake so that
yeah, but you need to I mean, you need to interpret definitional equality differently. So you cannot think of the equality of the model as the definitional equality of the formal system anymore.
You can start by trying to interpret a combinatorial logic, propositional combinatory logic categorically in a proof relevant way.
Yeah, that's a good suggestion. Maybe, yeah, in this way we can test these judgmental type theories on this as well.
Good. Are there any more questions from the audience? If not, let's thank the speaker again.